Start the recording, please. Hi, and welcome back to Codex. Today's speaker is Professor Nadav Dym from the Technion. Professor Dym studies problems in machine learning and computer vision using techniques from pure math like invariant theory. Today, he will tell us about efficient invariant embeddings for 3D point sets. Take it away, Nadav.
Okay, thank you. So yeah, I apologize in advance if we have a little bit of background noises. I'm at home and a lot of screaming kids around. It's 8 here, 8 in the evening. Okay, yeah, so let's start. Okay, so first of all, these are my collaborators, Stephen Gardler from Harvard, Talamir and Sneer from the Technion. And okay, we're gonna basically a math talk, but a little bit of invariant learning motivations. Okay, so what is invariant machine learning? We have some sort of task, let's say, the most classic example, classification of images. And you have some sort of symmetries inside this. This task has some symmetries. You're trying to learn some function f, this classification function. If you translate the image, it shouldn't make any difference. And therefore, it would seem reasonable to try to find, you're looking for f inside some hypothesis class, and you'd like that hypothesis class to have the same symmetries as the function you're looking for. Okay, so for images, a good example for that is convolutional neural networks, which at least more or less respect symmetries to translation. There are several other examples. For example, graphs. They have permutation invariants. So if you relabel a graph, that shouldn't make any real difference. So, okay, here's one graph. It's represented by some adjacency matrix. If I just take the yellow and orange vertex and change their order, suddenly it's represented by a very different matrix, but you'd like your algorithm to know that these two matrices are actually the same. They represent the same graph. And so that's an important example, but for us, the main example today is going to be invariant networks to point clouds or point sets. So a point set is going to be just a collection of n points in R3 or in RD in general, which the examples, it could be useful for several things, but we can think of them as, let's say, representing some 3D object like this chair, okay? And okay, so we have endpoints in R3. And if you think of some tasks, let's say classification, so it also has some symmetries like rotations. And okay, so we will sometimes think about orthogonal transformations where you're also allowed to reflect, or sometimes we don't allow reflections. So you have a special orthogonal group with rotations with determinant 1. And then there's also another thing is permutation invariance. So again, the point sets don't come with any natural order. If you say change the order of the first and second points, shouldn't make any difference. So that's another invariant we'd like to take into account. Okay, and so we'd sort of like to talk about either rotation symmetries or permutation symmetries or both of them together at the same time. Okay, so these are sort of various different instances of more or less the same issue. And again, so in terms of algorithms or networks that people have proposed, there's a lot of work also on discussing permutation invariant networks, also networks which are simultaneously invariant to rotations and permutations. This is just a partial list of some of the more well-known ones. Okay, so that's sort of the background, the field and invariant learning. What I want to talk about is sort of some math behind it, which also gets discussed in these papers a lot. So you can think of the goal we'd like to have as a universal invariant architecture. So, okay, we have some group we want to be preserved. We have some symmetries for some group. We have some function space which contains continuous and invariant functions, and we'd like it to be able to approximate any invariant function. Okay, so that would be our goal. So we'd like to have like a complete hypothesis class which can approximate anything. right? Sort of in terms of, the more well-known universality theorem of fully connected neural networks. You can think of that as, right? So that's sort of saying that any continuous function can be approximated by fully connected networks. So here we're talking about doing the same thing, but we're looking at some subspace of continuous invariant functions, and we want to have some hypothesis class which only contains these functions and can approximate all of them. Okay, so that's, in a way, that's our goal, although we'll sort of reduce that to a different goal. And then, okay, a little bit of technical assumptions. So we're going to have a group acting on V. G is the group, V is V, and we call that nice if V is a real finite dimensional vector space, and G is a compact subgroup of these transformations, linear transformations acting on V in the standard way, and the map which takes GV to G times V is polynomial. Okay, so for example, V could be RD times N, so matrices, or point clouds, and G could be the group of rotations and permutations. And the action we have here is you take X from your V, you multiply it by a rotation from the left and a permutation matrix from the right, and that's polynomial. It's linear in X. So in short, all the examples we're going to want to talk about are going to obey these assumptions. I think I should also have said that G, this group G, is sort of defined by polynomial equations, but I forgot to write that here. So let's say the rotations obey the equations RR transposed equals identity. Okay, so anyway, these are our technical assumptions. And under these assumptions, we want to, I should say, almost anything we're going to say can actually work with more general assumptions, but we can work with these and it will be fine. So let's just do that. Okay, and I think one could argue that the standard approach for having invariant universality of some sort usually uses some sort of version related to the generator of the invariant ring. Okay, so this is a classical theorem by Hilbert from the 1890, which says that for, under some weak conditions in the group, so for example, if the G acts in V and the group action is nice, then there exists a finite number of invariant polynomials, which basically can be used to define all invariant polynomials. So okay, we have this finite number of polynomials, F1 to Fn, and any other polynomial is just a polynomial. Any other invariant polynomial is just a polynomial in these things, in F1 to Fn. Okay, sort of in the algebraic language, this means that they are the generators of the invariant ring. Okay, so that's sort of a useful result. Okay, and as a result, basically since, okay, so we know that in general, polynomials can approximate continuous functions, and it turns out that invariant polynomials under our conditions can approximate invariant continuous functions, and neural networks can approximate that. So at the end of the day, you have that any continuous invariant function can be approximated by composition of a neural network and the invariant functions. Okay, so that's sort of one thing you can do. And then you could ask, okay, what possible issues could be. First of all, maybe, can we explicitly compute the generators? Okay, do we know what they are actually for a group action we're interested in? And often the answer to that is yes. So there are various results in invariant theory called the fundamental theorem of this group or that group, and they have characterization. Another question could be how many invariants we actually need. So what is capital N? How does it depend on the dimension of V? And okay, maybe the main point of this slide is that often this is very bad. So often N, the number of generators can be much larger than the dimension of V. Okay, and another question we could ask, so I've heard Dustin talk about this, is if our polynomial is the greatest thing to be using here. That's, in practice, are we going to use polynomials, and do we want to do that? But for now, let's ignore that. Maybe we have some, maybe discuss it later, maybe not. Okay, so that's that. So I said the number of generators can be bad. Okay, so let's just look, right? We have our action and R d times n. The dimension is n times d. Here's a list of, for the various group actions, how many generators there are. So let's say for the action of the rotation in R d times n, the number of generators is n squared, which is already often more than n times d, because often when d is smaller than n, which in applications is often what we're interested in, that's a pretty large number. And then if you're looking at SOD, suddenly you have much more generators, and SN similarly. SN is permutations. Okay, and for these last two group actions where we combine rotations and permutations, I don't personally know what the generators are, but maybe someone knows. Okay, but in any case, so these numbers are big, and later we'll see how we're going to fix this. Okay, right. So an idea which I think, we're sort of trying to push, me and other people here maybe in this room, is to try to replace generating invariants with separating invariants. So that's also a term from, I guess you call it computational invariant theory, I guess. Okay, so here's a definition, first of all. We have a group acting in V. We have a finite number of functions, h1 to hm, and we call these separating invariants if, first of all, if they are invariant, and secondly, if they're separating, which means that if two different elements in capital V, little v and little w, get the same value for all of the different h's, then this implies that w and v are the same up to a group action. Okay, so that's okay. So sort of these separating invariants completely characterize the quotient space. Okay, let's see an example. Okay, so let's say we have our group rotations in 2D, and it's acting in R 2 by 2 just by rotating, right? So this is like 2 by 2 point clouds. Okay, so what invariants do we have for this type of action? So one idea could be, let's say, we could look at the norm of the first point. So that would be invariant to rotations, or the norm of the second point. Okay, those are both invariant, but they're not separating. Why not? Okay, both of them together are still not separating. So for example, if you look at, okay, this pair of blue points, these are this is basically an element in capital V, and it will be, okay, you can rotate it to get the two green points, but not to get the two red points, right? Now, however, with respect to these two invariants we just defined, the norm of the first and second row, column, whatever, you get the same result, right? So according to these invariants, these invariants can't witness that these things are different. However, if we add one more invariant, let's say the distance between the 2 points, okay, so then these three invariants together are separating. Okay, so that's an example. Okay, so we have separating invariants, we have separating versus generation. Okay, so we're trying to say at the end of the day that separation is what we need, right? So one important thing is, if we go back to our argument before, where we said we can approximate any continuous invariant function using compositions of neural networks with the generators, then what we really need, and happens to be true, is that if you replace the generators with continuous separating invariants, then you have the exact same characterization, where now you replaced the generators with separators. So in terms of universality, we're good. Is there a question? No. Okay. What else? One second. Okay. Another small point is the generating invariants are, under our conditions, separating. There are more separating invariants than generating, so hopefully maybe we can do better. Okay, and the most important thing, though, is that actually, while the number of generators can be very large, the number of separating invariants, we can control it rather well. So the number of separating invariants is always, at most, twice the dimension of our vector of space plus 1. Okay, so that's a general theorem. And it's also, that's not only an existence theorem, it's sort of also a little bit constructive, more or less constructive. So the way it works in general, in essence, is that you take whatever, say you have some larger collection of separating invariants, for example, your generators, right, which we know exist from Hilbert's theorem. And then you take linear combinations of those, random linear combinations, and with probability, up to a Lebesgue set at 0, this set of WIs will define separating invariants, and the number of random separating invariants you need will only be this twice the dimension plus 1. Okay, so in essence, this gives you an algorithm which is like a projection algorithm. You can first have to take your V and compute all the values in your expensive generators or some other separating invariants which you already know. And then you can project down using random linear projections, and that will be injective. But in terms of computation, that's sort of so and so, because you still need to go through this expensive intermediate step. Okay. So our conclusion so far, right? So this is a table we're going to be taking with us along the way. We have our various different examples. So for now, we can conclude that we always can work with twice the dimension plus 1 separators. So for us, we're talking about point clouds. The dimension is 2 times n times d. I mean, the dimension is n times d, so twice the dimension plus 1. Okay, so we can be content with a small number of separators. The complexity, if we're just going to linear project, is going to be certainly larger just than the number of generators, and even that number is very big. So in terms of algorithms, we're not so happy maybe yet. Okay, so what we want to do is improve this using some sort of trick which we're sort of generalizing or borrowing from phase retrieval. Okay, we're going to focus on this first example, SOD. Second example, I guess. Okay. So here we have, right, again, the same, we're talking about point sets, endpoints in RD. The action is, you're rotating with a matrix which is orthogonal with determinants 1. And as we sort of mentioned before, there's a very large number of generators, which are, so you can look at the pairwise distances between all points and the norms of points and determinants of d by d submatrices. Okay, we're assuming d is smaller than n. Okay, so that all of these together are generators. Again, we got a lot of those. Okay, we'd like to do better. And our sort of methodology to do that, as we try to look for a continuous family of invariants, which often you can just build from these generators too, in a way. Okay, we're going to define this new sort of function, parameterized function, where we take linear combinations of the points, take their norms. That sort of corresponds to what we have here. And we take determinants of the matrix X multiplied by some weight matrix W. Okay, so what the point is, these each for any choice of the parameters, little w and capital W, this thing is also an invariant. And what we'll be able to say is that if you choose randomly 2 nd plus 1 such invariants, then you will have separation. Okay, so basically, if before we were talking about mapping up and linearly projecting, that was one kind of random measurements. Here we have a different, sort of a different type. And in this type, we don't have to compute everything and then project. We can, it's more efficient. Okay. So what ends up happening is that we can compute this number of separators, but since we're not going to project, map up and project, the complexity will only be something like n times d squared, the complexity of computing this. Again, when d is smaller than n. Okay. So now let's sort of try to explain why or where this comes from. Okay, so we have, so we said we have this sort of continuous family of separating invariants. Let's define what that means. So family is a continuous family of separating invariants if we have that for every choice of w, the function defined by w is invariant. So we have this. And we have separation, which sort of like before means that if you have two elements which are not related by group action, then you can find some parameter w for which you can separate. Okay, so again, if we compare this to our definition of separation before, this is just like saying, instead of having a finite number of separators, we have a continuous number, and the rest is in a way the same. Okay, and then what we can prove, again, sort of based on this phase retrieval concept, is the following. So let's say we have a nice group. We have a continuous family of separating invariants, which for now we're going to assume are polynomial. And then we can say that if we choose twice the dimension plus one invariants, then this function will be separating. Okay, so that's the theorem, a slightly weakened version. We'll strengthen it a bit in a minute. And then a bit of remarks about that. So one thing is that this cardinality is usually not optimal. So usually you can do a little bit better than this, but that usually is not. It's not a general thing. Like you have to, in case whatever specific group action you're interested in, you have to sort of investigate it more carefully. And again, this proof idea comes from this paper, where sort of in a sense they prove this for special invariants which are related to phase retrieval, phaseless measurements. Okay, I'll continue in a second. Maybe questions, if there are questions, maybe it's a good point to ask. I don't know. Okay. So move on. Okay, so we said this is our theorem, a little bit how we can sort of strengthen it a bit. So one thing we can do is that this capital V, which we defined as a vector space, really it could be some low dimensional subset of some higher dimensional vector space. And as a result, the number of invariants we're going to need, one sec, let's go back a bit. So the number of invariants we're going to need will just be like twice the intrinsic dimension. If we're only interested in separation in some small subset, the number of invariants will be proportional to the dimension of that subset. So that's a useful thing. Another thing is that we sort of mentioned before that we don't like polynomials in particular, for sometimes. So we can also replace this with semi-algebraic mappings, which is sort of much more general term, which includes, besides polynomials, also rational functions, piecewise polynomials, in particular piecewise linear functions like neural networks with ReLU activation, stuff like that. But that comes with a small price where we actually have to replace this notion of separating with something called strongly separating, which maybe we'll not go into unless someone really wants us to. Okay. Well, that's that. Now let's see another application. So we sort of talked about SOD before. Let's see a different application now for permutations. So here, right, again, we have endpoints in RD. The permutation action is relabeling. And what we're gonna sort of split this into two cases, or start with the case when D is 1. Okay, so we only have n basically numbers. And in this case, we have the number of generators, which I was always telling you how bad it is. Actually, in this case, is not too bad. So when the dimension is 1, so you have n generators. For example, you can take the sum of n points and their sum of the points squared, and other powers until you get to the nth power, or n is the number of points. And these are generators, so they're also separating, and that's good. Okay, so we have a good cardinality when d equals 1. So we're not going to fight this, we're going to use this. The issues will start. Okay, we can also call this capital F of x, so sort of vector value mapping. Okay, and then, okay, so we have this. Now, what happens when d is larger than 1? Then the number of generators becomes very big, so we're not happy with that anymore. And what we can do instead is try to build a continuous family of separators, and then we know that we get the right cardinality and everything. So the way we do this is as follows. Okay, let's imagine we get two vectors, x1 and 2 point clouds, x1 to xn and y1 and yn, and they're not equivalent up to permutation, which essentially this means that as sets or as multisets, they're not equal. Okay. Now, our idea is, okay, there are other ideas similar out there. Anyway, there's to sort of take this set of vectors and project it down to 1D. Okay, so you take some random vector in RD and you apply it to your set. And now you have a set of n numbers. And this, there's a certain, it may be that now these two things are the same, but for almost every A, they will not be the same. So the set of A for which this will be equal is a very small set. It's like a union of subspaces of RD. Okay, so that's good. And then, okay, we apply our F. Our F is the generators we had before. You put in there a set of numbers, and it injectively maps it. So it's permutation, invariant, and injective for sets of numbers. Okay, and that gives you a vector in Rn. And then essentially you are in a way finished, but we'd like this to be more efficient, so we project down again. Okay, so we have two vectors in Rn which are not the same. Apply a linear projection, we get a number. And again, for almost every B, this will not be the same, right? And so the conclusion of all this is we defined some function h of x with parameters a and b. And this function is an Sn invariant function, and it's a separating family, which means, again, that if you give me two different x and y, the probability of having a and b which don't separate them is 0. Okay. And just as a small remark, we can also, a different thing we can do is instead of using this polynomials, we can use sorting. And that has, in a way, better properties. And so sorting is not a polynomial, it's a piecewise linear function. But as we discussed before, we can use these things too. So we're okay. Okay. Sorry. Okay, so then, okay, so well, maybe I should have, okay, maybe I should have added this step here, so I'll add it in words. So, okay, so right, we're at this step. Now what we want to say is that if we now randomly choose the right amount of invariants of parameters here, so twice the dimension plus 1, then this will be separating. Okay, so at the end of the day, we get twice the dimension plus 1 permutation invariant separating permutation invariants. And the complexity of computing these when you use the sort version is n times d plus log n. Okay, good. So we're already close to the end. This went a little faster than it did last time. Okay. Okay, so the end is sort of trying to fill in this table and a little bit of experiments. Okay, so the OD case, you need, so we'll get something similar. The case of where you have rotations and permutations together is sort of harder, seems. Also, we know that when if D and N are going to infinity, that sort of becomes as hard as graph isomorphism, and so it's not so easy to deal with. And what we know how to do is to compute these things with a complexity of n to the power of d. This is sort of a separate paper already. And I've sort of skipped all the part of how we do that. But I just want to show some experiments related to that. Okay, so we're imagining that we have some way of separating here. And what we're going to try to look at is just an experiment where we try to see how much this impacts, architectures. So. Okay, so what we have here, we have a sort of chemistry-based task where you're given a molecule, which is, let's think of it as a point cloud. There's also some sort of graph-like information there. And you're trying to there's a sort of expensive simulation that some people ran for us to give us training data, which gives some chemical properties of the molecule, but we want to learn it. So that in the future, we'll be able to infer from the molecule its chemical properties much, much faster, right? So this is the general task. We're working in a data set called QM9. We took some architecture, which is rather successful and for this type of task called EGNN. It's a permutation and rotation invariant. It's not separating. So there's actually a paper where it shows that it's not separating. And we sort of fixed it so that it is. Again, there aren't any details here about how we did that, but we did. And we tried to see how well these two architectures perform in terms of this regression task. And we get a sort of mild improvement in most of these goals, not all of them. So that's nice. Still, we do, I think we also believe that there should be tasks where this will be more helpful. So part of, I don't know exactly, we have, the proof is in the pudding in a way, but sort of believe that a task where you want to be, here you're basically mapping your molecule into 10 numbers or 11 numbers, I don't remember how many numbers to count. So separation may not be so critical. It may be more important when you have, let's say, something like an invariant autoencoder, where you actually have to be really injective to do perfectly on this task. Okay. And then the last thing is, okay, just an apology for what I'm not discussing. So, okay, so one important thing which is discussed in other papers is stability, right? So you have this notion of invariant and separating. It essentially means that you have a mapping which takes your quotient space to Rm, and it's injective. So you have an embedding of your quotient space into just Euclidean space that allows you to work in Euclidean space. But you would like this mapping to be by Lipschitz in some sense. So you have this, arguably is a natural metric on the quotient space. So you have two orbits in the quotient space. The distance between them will just be, the best you can, by applying one group transformation, make them as close as possible. You'd like to sort of preserve this distance, right? And again, so some of the guys here, we have some papers which discuss this more, but I have nothing to say about that right now. But we should, it's worth discussing. And yeah, I guess that's it. Thanks.
Okay, thanks. Let's thank our speaker by clicking you all know what you're doing. We've been doing this for a few years now. Okay. Yeah.